Quantitatively, the entropy of a system is equal to Boltzmann's constant times the natural log of W, where W equals the number of energetically equivalent different ways the energy of the individual molecules or particles in the system can be arranged. Let's take a closer look at W. How do we actually calculate the number of energetically equivalent different ways the energy of the molecules in a system can be arranged? We're going to start with a very simple system where we have a container of fixed volume and there are two gas particles in it. We're first going to divide that container into 4 different regions. In the first example, we're going to put a barrier in the center of the container that will keep the gas particles on the left side. Let's calculate how many energetically equivalent different ways there are to arrange the gas molecules in this system. The first configuration has both gas particles in the top left side. The next configuration that's equivalent energetically would have both particles in the bottom. The next configuration would have the red particle in the top region and the blue in the bottom. And the last energetically equivalent configuration would have the blue particle in the top and the red in the bottom. Here there are 4 energetically equivalent different ways the molecules can be arranged in the system. You can see that it's fairly straightforward if there are just 2 gas particles that we're talking about. But in chemistry, we're often discussing something like Avogadro's number worth of particles. So instead of drawing a picture, it would be convenient if there is an equation. The way we calculate W is that W is equal to the number of cells available to particle A raised to the number of particle A's. In the case where there are multiple particles, we simply multiply the term for the particle A's times another term for the particle B's and C's and D's and so on. So let's use this equation for W to calculate W in the case where there are 2 gas particles in a 4-cell box divided in half. W would be equal to, for the, let's say, red particle, there are 2 cells available to that particle, and there's 1 particle. So that's 2 raised to the 1 multiplied by, for the blue particle, there are also 2 cells available and 1 particle, so that's 2 raised to the 1. 2 raised to the 1 times 2 raised to the 1 equals 4. Let's calculate W for 2 gas particles in a 4-cell box. In this case, it's not divided in half. It turns out that there are 16 different permutations of this possible configuration. So W equals 16. Here I've drawn out all 16 configurations, but it's much more straightforward to use the equation above and calculate W. To calculate W for this system, we see that there are 4 cells available to the red particle, so that's 4 raised to the 1, multiplied by 4 cells for the blue particle, and there's 1 particle raised to the 1. 4 raised to the 1 times 4 raised to the 1 is 16. Let's redo this calculation for a slightly different scenario. In the previous example, we had gas particles and they were free to move throughout the container, and more importantly, they were free to occupy the same kind of quadrant or region of space. In this example, we're going to do a calculation where we have gas molecules adsorbed to a surface. Only one gas molecule can occupy an individual site on the surface, so we can't have double occupancy. Let's look at a similar surface where there were 4 possible locations. We'll restrict the surface, so we'll put a barrier so the gas particles can only occupy the sites on the left half. Looking at this picture, we see that W is 2. There's one configuration where the red particle is in the top surface site and the blue is on the bottom. And then the second possible energetically equivalent configuration is where they flip positions, where the blue is on the top and the red is on the bottom. Because these are individual adsorption sites and double occupancy is not allowed, there is no other possible configuration. Let's calculate the value of W. To calculate W, we should think about populating the surface in a stepwise process. First, let's place the red particle. The red particle, if it was placed first, has two different surface sites, or two different cells it could occupy. Therefore, the cell number is 2, and there's one red particle, so that's 2 raised to the 1. The next step would be to add the blue particle. Because one of the cells is already occupied, the number of cells that the blue particle could occupy is 1. And there's one blue particle, so that would be 1 raised to the 1. So W is equal to 2 for this system. Let's redo the calculation for the two gas particles adsorbed to individual sites on the surface, and let's remove the barrier between them. Here is one possible permutation of this system, where the red particle is in the top left corner and the blue particle is in the bottom right corner. Let's calculate W. Again, we should think about populating the surface in a stepwise process. Let's add the red particle first. When we add the red particle to the surface, there are 4 possible cells that it could occupy, and there's 1 red particle. Next, let's add the blue particle. If the red particle is already on the surface, that means there are only 3 cells available, and there's only 1 of those particles, therefore that's 3 raised to the 1. W for this second system is 12. Let's return to our quantitative definition of entropy. The entropy of the system is equal to Boltzmann's constant times the natural log of W. Let's calculate the quantitative value of the entropy for this system where W is 12. When we plug in the values, we see that the total entropy for this system is 3.43 times 10 to the negative 23rd joules per Kelvin. You could also calculate the change in entropy for a process where you had 2 gas particles adsorbed to individual sites on a surface, where half of the surface was available, and then what is the entropy change when you remove the green barrier and allow the particles access to the entire surface. The change in entropy is the entropy of the final state minus the entropy of the initial state. We can also plug in our quantitative definition of entropy, where it is Boltzmann's constant times the natural log of W. That would simply be Boltzmann's constant times the natural log W final minus natural log W initial. If you remember from your log identities, the subtracting 2 logs is division within the log. And so you could simplify the delta S formula this way.